sure what the
This is the way to make
people see
the
fit
one
the
there is
way.
I'll just try.
Yeah, just try again.
by chance, if that when you started up there, it was good, baby.
There you go.
Ah. Alright.
Right, should we pick up?
Sure. Alright. Okay, hello everybody. Samson's now going to continue his lecture series on contextual semantics.
Thanks very much.
In the middle of things. Yes, my attempt to be, as they say, the rotel is paid with good intentions or something, so in my attempt to show a calculation of how one calculates a bell table yesterday, I got slightly off my timing, so we're sort of slightly in the middle of things, but hopefully we can get back on track. So what we were doing, having seen concrete examples of what we could understand as observational scenarios that we can imagine and which we could prove, could not be explained in terms of a classical mechanism. This was the idea of a classical source that we discussed yesterday, which is actually a sort of thinly disguised version of what is usually called a local hidden variable model. So we could not use such a mechanism to explain that kind of behavior, and yet we could see that quantum mechanics would predict such a behavior using an entangled state as a resource. So that was a sort of specific place we got to. We'd already shown, in effect, in a fairly potentially quite general setting, one of the major no-go theorems of quantum mechanics, the Bell's theorem, which more positively can be seen in many ways as the starting point for the whole subject of quantum information. And what we were starting to do yesterday, and will continue to do now, is to extract from this some general mathematical structure in which we can see the nature of these results in a broader context. And this will lead on the one hand to being able to make some finer distinctions which will have connections back into quantum information and quantum foundations, but it will also allow us to see the same structure operating in apparently completely different settings, actually a number of settings which are quite familiar in classical computer science. So that's the way we want to carry on today. We were starting to assemble the ingredients for this yesterday. So one ingredient was this family, so we have an underlying set of measurements, one of the ingredients that we started to have was this idea of a measurement structure, which is a family of measurement contents. So this was just a family of subsets of our set of measurement labels or variables. And we could see that indeed in this Bell scenario, Alice and Bob, this was a particular, actually rather simple example of such a cover. If you think of it as a hypergraph, it's a very simple kind of hypergraph. But we could also consider much more combinatorially complex things, some of which come up very naturally also in quantum mechanics. So in particular the Cauchy-Specker theorem, which I think you've heard about in John's lectures, where we take X to be a set of vectors, or labeled by a set of vectors, and we form those subsets which are unit vectors, let's say. We form those subsets which are mutually orthogonal and hence form an orthonormal basis. And this can be combinatorially quite complex. Here is a particular case of such a family of sets. We have 18 elements labeled by these letters, and we have 9 sets, each set containing 4 elements. The point is that it is possible to label these letters with vectors in R4 such that the vectors in each column are orthogonal. This is and this yields a proof of the Cohomological theorem. This is actually often taken as one of the most economical witnesses for quantum contextuality. It's a construction due to Cabello and some co-authors. We'll come back to Cohomological theorem I think next time. But what I want to do is to, before we march ahead, just to recap on this underlying mathematical structure. Since we're all happy with functors, we can say it loud, say it proud that we have a functor here. So in particular, we're making use of this simple kind of distribution functor. And there's a bit of generality here which will be useful for our purposes. So the generality comes by taking as a parameter of this construction a commutative semiring. So something that has addition and multiplication, which are commutative and associative and have units, and the distributive law, but we're not assuming inverses for either addition or multiplication. And three examples that are of particular interest to us are the non-negative reals, just the Boolean algebra 0, 1, and the reals, which of course are a semiring and much more. And then a distribution, an R distribution on a set is a function which has finite support, meaning that it only sends a finite number of elements to other than 0, and whose total weight is 1. And of course this makes sense because only finitely many of these are not 0. So that's what we mean by a distribution. And in the case of the non-negative reals, we see that this exactly gives us the probability distributions of finite support. In the case of the Booleans, 0, 1, it gives us the non-empty finite subsets. So finite because of finite support, and non-empty because of this normalization condition, which of course here we're taking the sum in this case to be the disjunction or union. And in the case of reals, it gives us normalized signed measures. And this construction extends to a functor, which allows us to push probability measures or distributions on x forward onto distributions on y along such a function f. So if I got a distribution on x, and I have this function f, then in a natural way I can look at y, and for a given element of y I take its inverse image under f, and of course the distribution I already have, d, tells me how to assign a weight to that subset just by summing over the elements of the subset. Okay, so that gives me a push forward action, and it's easy to check that this is functorial. In fact, it's more than a functor, it's actually part of a monad, a well-known and studied monad in computer science. It's often referred to as a discrete version of the Curie monad, although strictly speaking we're insisting on finite support here. It's not quite, the terminology doesn't quite coincide with the usual probabilistic function. Now from our point of view, this functor is a gadget that we can combine with this other piece here, which is just the thing that, given a set of measurements or variables, as we may think of them more generally, gives us the set of all assignments from that set of variables into a fixed set of outcomes. And of course this is a functor, a contravariant functor. It's the contravariant Hom functor, which incidentally was playing quite a starring role in Prakash's lecture yesterday, because that's with this thing with a schizophrenic object, exactly how you get from one category to another contravariant. So this is a very standard thing that's a functor, and then if we compose it with this covariant functor, what we get all together is a contravariant functor from the power set of our set of measurements opposite, so it's a contravariant functor into the category of sets, and such a thing as a pre-sheaf. And that's our basic gadget. And in some sense, we can say that this gives us a natural setting for contextual probability.
Samson?
Yes?
You can actually say a bit more and say that this functor f goes into the Eilenberg-Moore algebras of the monad. Is that useful?
It hasn't been useful to me yet, but I agree, and it's of course, so far the monadic structure of the functor has not played a big role, although I should say that it's possible to be more abstract than I am being. And one of the things I had to do in sort of trying to communicate with people in quantum information was to learn to be less abstract than I instincts would usually be. So actually a lot of the things we're talking about can be done at the abstract level of an affine monad.
Right.
So then this becomes highly relevant.
Yeah.
However, it turned out to be also to be easier to relate it to some of the concrete issues in quantum information, to go down a level of generality and be more specific. But I agree that is all, as it were, waiting for us, and we may come back to that actually a bit later. Now, the point I wanted to make here is that we can see this gadget as a natural setting for contextual probability theory. Now, what do I mean by that? Classical probability theory, the setting is you have a sample space, so you know what your events are, you know the things that can happen, and then you assign probabilities to them. And there's a single fixed sample space. This setting naturally gives us a sort of little world where we can think that the sample space itself is varying. There's a functorial variation over the sample space, and that's exactly what's going on here. As we look at different measurement contexts or different sets of variables, then we're assigning probability distributions on the valuations for those sets of variables. And this variation has some decent structure in that it's functorial. So this is a very natural setting for contextual probability theory, and it's contextual exactly in the sense in which, as it happens, quantum mechanics is contextual. That we have to take seriously the measurement context that we're using, because in general we can't assign values to variables which are independent of the measurement context that we're considering. If we could, we'd be non-contextual, and quantum mechanics is telling us that we can't. Okay, so continuing with this basic mathematical setting, here's our basic setup then. So that's in the background, this gadget for contextual probability theory. And then our basic setting, we can call it an observational frame. I'm just looking at the frame here. No, I can't remember what, anyway. So I can't remember if we've agreed on some term for this, but anyway, so let's call it an observational frame. So it's what we were discussing. We have a set of measurement labels or variables, and in all the examples we'll look at, by the way, this will always be finite. So you could even say this is quite embarrassing from a mathematical point of view, and yet there's a lot of non-triviality here, and actually all the discussions of all the proofs and discussions of Bell's theorem and related topics in quantum information and the Coach-and-Specker theorem and many other things that arise in the field, we do consider finite sets here, finite numbers of settings. And if you think about what we can actually do in a lab on the nth day of the universe, we will still probably only have a finite number of settings for our instruments. Then we have this family of subsets, with what we're calling the measurement context. So combinatorial is just a family of subsets of this given set X. It's a hypergraph. And we do ask that every element of X appears in at least one of these sets, so the union covers the set. And then we fix some set of outcomes. It's always possible to go to a slightly more refined approach where you have a different set of outcomes for each of the variables, a kind of typed version, but it's just simpler to munge everything together into one set. And then we have this commutative semi-ring of weights, as we've already seen, and then we can define this pre-sheaf exactly as we were just discussing. This pre-sheaf uses the semi-ring, it uses the set X, but it doesn't yet use this set of content. So this is the general setting for contextual probability. Now where does this measurement structure, this family of subsets come in? It comes in defining a model, what we call an empirical model. We can think of this as a little observational window on the world, and in some sense, if you take a physical theory, for example, then in terms of how it connects up to sort of experimental observation and confirmation, it does so by having little empirical windows where it makes specific predictions. And in the case of basic quantum mechanics, the basic predictive content comes through the Born rule, which we looked at briefly yesterday, and then we can make tables of the kind that we were looking at yesterday. And this notion of empirical model is abstracting and generalizing from that idea of a table. Alice's measurements, Bob's measurements, their outcomes, the probabilities we assign to these things. So what is an empirical model in the setting of having this structure here? So now it's relative to this cover, this set of contexts. And that's also why it's empirical, because we're thinking that this set of contexts is a set of actual measurements we could perform together and hence get empirical data about and get probabilities for the possible outcomes. So it's a family of distributions. I'm varying my notation a bit here. This is the same thing as the pre-sheaf we were talking about here. This way of writing it reminds us that it's built out of two pieces, the distributions functor and this valuations on the variables in the context. So it's a family of distributions, one for each context, and that's just like the rows on the table that we were looking at. So for each choice by Alice of a measurement and Bob for a measurement, that picked out a row of the table, and on that row what we saw was a probability distribution on the joint outcomes. That's what these guys are, but in a more general form where it could be for any context in this potentially richer combinatorial structure. And the condition that we impose is that they're compatible. And this is compatible in the geometric sense, that they agree on their overlap, on their common variables. And the thing that gives us the language, exactly the language to express this, is this restriction, which is part of the fact that this thing is a functor, as we've seen. This gadget here is a functor. So we can take, for any context C and C prime, we have one distribution, one row which is over context C and one row which is over context C prime, and it's a consistency condition. Do they agree on their common part? Well, the common part is the intersection of the two contexts, what we're saying is when we restrict this one to this intersection, we get the same thing as when we restrict this one. And now we come to a first, and this is, by the way, exactly the standard way you talk about compatible families in the world of sheaves. If you're asking if a pre-sheaf is a sheaf, you're saying, can compatible families be glued together? And compatible means in exactly this sense. So the classic picture, did I have this? Yes, here we are. This is the classic picture where we have little functions defined, so it could be on open subsets of some space, and the point is, can we glue these functions together? And provided they agree on their intersection here, then we can define it consistently on the union. So that's the sort of paradigm for this notion of compatibility and then being able to glue compatible things together. Okay, so we have this idea of compatibility. Now we come to a nice point, which is that this geometric idea of compatibility coincides with, or at least in the cases where it's commonly discussed, things like the Bell tables we were looking at, exactly coincides with, and we could say generalizes then, a very physically important condition, which has been fundamental in all the recent work in quantum information and quantum foundations, namely the no signaling condition. So the no signaling condition is motivated by physical considerations. And it's to do with the fact that, as we were saying, Alice and Bob are, we think of them as, in principle, being space-like separated. So they're far enough apart that when Alice does her measurement, there's not enough time for any information about this to propagate to Bob while he's doing his measurement. So therefore, what we take as a principle from that is that the statistics that, for example, Alice sees in isolation when performing her measurement should be independent of which measurement Bob happens to choose. And symmetrically, of course. It's a symmetric condition. So that's the physical condition. And we can translate that in terms of the probability tables we were looking at into saying that the marginals, if you marginalize to get just a probability for Alice by averaging over the, summing over the possible outcomes for Bob, then it doesn't matter which choice of measurement you take for Bob. When you take the marginal to get a probability for Alice, you should get the same thing. So that's giving us a form of independence of Alice's statistics from what Bob is doing, and vice versa. So that's physically the no signaling condition. But the nice point is that this is exactly what our geometric condition says. So just to see this, let's look at the bipartite case. This is where one would usually see the discussion explicitly in the quantum information literature. So Alice is proposing to do her measurement, call it M sub A, and there might be two choices for Bob's measurement, either Bob MB or M prime B. And then what we're saying is that the probability that Alice sees some particular outcome for her measurement is the same whether we look at whether we sum over all the possible outcomes for Bob choosing his first measurement. So we have this first context here where Bob chooses this measurement MB. So when we take that sum, it should be the same as when we take that sum. But you see, remembering the way that we defined restriction for these distributions, restriction essentially was marginalization in the case of probabilities. So that's exactly what this geometric condition is saying when applied to this situation. So the probability for Alice to get her particular outcome is the same, whether we marginalize, whichever measurement that Bob might do, we're marginalizing over the possible outcomes. That's what it's saying. Right. So, we discussed yesterday this idea of a classical source, which kind of, I think, makes sense independently of physical considerations. A nice point is that essentially, with a very minor change of vocabulary, this is one of the nicest pictures that's been given of what a hidden variable model looks like. Actually, the well-known paper by David Mermin has written a number of very illuminating papers on these results in Foundations of Quantum Mechanics. So this is what he calls the instruction sets picture of hidden variables. So you see, it's almost identical to the picture we looked at yesterday with the classical source and the local registers and Alice and Bob and so forth. So the idea is that now we think of Alice as performing measurements and choosing settings. Bob is performing measurements and choosing settings which spin direction to measure in and so forth, as we were saying, and they have these joint outcomes. And the way we could try and explain the statistics of what they see in their joint outcomes is by postulating now a physical source, as it were, nature, which is secretly, when we prepare the particles, it's labeling them with these instruction sets. And by the way, instruction set is Mermin's term, so he was explicitly using, actually in 1990, a computer science term to convey exactly this intuition. And what the instruction set does is to tell us for every measurement what the outcome is going to be. Just like the picture that we gave yesterday of actually writing into these local registers with particular values. And because we know that the outcomes are probabilistic, right? It's not a deterministic model. Again, we're assuming that the source itself has some kind of randomness. So which instruction set it chooses to label the particles with is essentially modelled by sampling from some distribution. And the point is that the source labels the particles with these instruction sets. The particles arrive at Alice's location and Bob's location. Alice chooses a measurement and performs it, and the instruction set says which of these things, which of these results we should get. This is exactly the discussion that Mermin gives of this, actually in his expository paper on the GHZ form of non-locality argument. Now, how does this fit into our geometric picture, into our correspondence with these sort of ideas coming from sheaf theory? So we're given this empirical model, and the question we want to ask, which is one of the basic questions you ask in sheaf theory, which is all about the passage from local to global behaviour, is does there exist a global section for this family? Can we glue this coherent family together into a single global entity? So if I've got this family of distributions, local distributions, varying over these contexts, can I find one distribution to rule them all, sitting in this total set of variables x, which gives us back all the constituent distributions by restriction? Okay, can I unify them into a single distribution on all the variables? So one of these things that is in here, so this distributions on this, what is this set? This is just the set O to the x. It's assignments from the whole set of variables into the set of outcomes. But that's exactly what an instruction set is. So that is Mermin's picture of the instruction set. It's a deterministic hidden variable in other terms. You may, of course, we're looking at probability distributions on these. Incidentally, yeah, okay, we'll come to that in a moment. Now, just to unpack this in the terms of our explicit formula for the restriction operation on distributions, this marginalization formula, this equation is saying that the empirically observed probability in some context C for some local set of outcomes just over the variables, the measurements in that context, well, if it's recovered like this by restricting this global distribution, then that unpacks into this sum, and you can see that we can write it equivalently like this. If I put an integral here instead of a summation, I mean everything's finite here, so I don't need to write. Then you see this is exactly the standard way one would write. Well, if you look at the sort of usual literature on hidden variable models, this is exactly the way one writes averaging over the hidden variables. So the hidden variables idea, I guess, historically goes back to the classical statistical mechanics of the 19th century, and the idea that you could recover phenomena in global phenomena of say, a thermodynamic system by averaging over all the microstates. So you have tiny little particles swarming around, which in principle are deterministic, but there are just too many of them for you to track them all. And then so you're interested in behaviors you get by averaging over all the microstates. And the hope was originally, with quantum mechanics, and this goes right back to von Neumann, at least, that you could, in a similar way, explain the the strangeness of quantum mechanics by averaging over some deterministic behaviors at a more fundamental level. And this is the kind of formula one's then led to write. And you see that what this unpacks into is exactly having this global section that you're recovering things by restriction from. Okay. And in fact, this does subsume the usual discussion of local hidden variable models, for example, as in Bell's paper. So essentially, Bell writes this condition, but with an integral rather than a sum. And you might think, well, I'm maybe being we're being maybe too restrictive in what our notion of hidden variable model is. Maybe we should allow a sort of a big set, maybe a measure space of hidden variables, maybe the hidden variable model itself shouldn't be ultimately deterministic. Why should it? But in fact, it doesn't make any difference. If you have this apparently more general notion of hidden variable model, in the end it will give you the same predictions once you do this thing of averaging over the behaviors as something of this form does. So this is a canonical form of hidden variable model that is fully general in terms of the behaviors it allows you to predict. So what we derive from this is the following statement that allows us to relate this geometric language of global sections to the classical discussion of hidden variables. The existence of a local hidden variable model for a given empirical model for some window on things we can actually observe, so the existence of a classical explanation, if you like, for one of these observational windows is equivalent to that sort of physical, well, it's a mathematical question, but it's directly physically motivated, is equivalent to this more geometric statement that this empirical model, seen as a compatible family with respect to this pre-sheaf, has a global section. And the significance of that is that by definition, what quantum non-locality or contextuality means, if you take the fundamental definition as we have it, is that no such hidden variable model exists. If it goes beyond what can be explained in that form, then we say we have non-locality if it's a Bell kind of scenario, and more generally contextuality. And that is strictly equivalent to this geometric question of whether there's an obstruction to the existence of a global section. Okay, so once we have this mathematical question, and the additional point is that we have it in a rather more general framework, as we've been saying. So it applies not just to the usually considered situation, say with Bell scenarios, but to a principle much wider class of things. So, given that one has this question and it's of interest, it's also interesting to know what methods one can use for showing obstructions to global sections. And we've already seen one in action yesterday, which was this kind of logical twist on Bell inequalities. Bell inequalities are one of the fundamental techniques in quantum information, since they originally developed by Bell and particularly by others, Walser, Shimoli and Holt and many others, as a means of detecting non-locality and quantifying non-locality. And there are literally thousands of papers in the literature that produce Bell inequalities and in various situations to answer various kinds of questions, to leverage them into various kinds of quantum advantage and so forth. Now, we gave this nice, and I hope you agree, rather simple logical way of deriving a kind of Bell inequality at the beginning of yesterday's lecture. And you might think that that was a sort of curiosity or some particular case. But in fact, it holds that every Bell inequality is equivalent to a logical Bell. In a precise sense. So I'm actually think I'll try and say more about that in tomorrow's lecture. And this was the subject of a paper with Lucy Hardy recently. So in fact, this way of generating inequalities to be satisfied by probability distributions based on logical consistency conditions actually gives a complete picture as to what Bell inequalities are. So that's a first method, and we actually used it to give our original sort of argument that there was no classical source to explain that table, the Bell table that we were looking at. A second kind of method is a kind of linear algebra or really linear programming method if we're interested in probability distributions, which is developed in this paper here. Well, there are some interesting aspects of that. Let me just mention very briefly that perhaps conceptually, I mean, something that needs to be developed further, but conceptually does show that this geometric picture that we've been discussing really does apply. Is that the language of sheaves that we've been using is justified. Is that with Shane Mansfield and Rui Barbosa, we looked at applying sheaf cohomology to detect contextuality in these kinds of empirical models. So in other words, topological invariance. So even though the underlying space is discrete, because you have a non-trivial sheaf structure, a non-trivial variation, then the structure of the check cohomology groups, specifically in general the sort of sheaf cohomology groups, is non-trivial, and one can define an invariant which is a necessary condition for non-contextuality. Something in these groups that could be uniformly defined vanishes if you're non-contextual, which means that if you're contextual, this is detected by the non-vanishing of this element in the group. So that becomes a witness for contextuality. And quite a lot of examples could be computed in this setting to witness contextuality in this form. I think there's certainly potential to take that a lot further. Okay, so what I want to do now is take this, rather than pursuing these things immediately, is to take this general setting and use it to analyze contextuality as we've been defining it a little more finely, to see that one thing we can do immediately, which this setting gives us the language to do, is to distinguish different levels of contextuality. So degrees of contextuality. So what we saw was, recalling what we did yesterday, was we started off with this Bell table that was a probability table, and we used an argument with one of these sort of with these Bell inequalities to show that it couldn't come from a classical, couldn't be generated by a classical source, that it was non-local. Then we looked at the Hardy construction, which, and as we observed there, we only need to look at the support of the table. We didn't even need to know what the probabilities were to see that non-locality did arise there. And there's a big literature, starting off with the famous sort of work Greenberger, Horn, Zeilinger, GHZ state, to consider showing forms of Bell's theorem and related results using without probabilities or without inequalities. So there's a big literature on that, and I think it's still not as clearly concepts haven't been made as clear as they could be, and I think having a general setting is advantageous in that regard, where we can see how to frame these things in such a way that a clear hierarchy emerges. So we have some model, which is we said what an empirical model is. We get these distributions valued in some semi-ring. Let's, for the sake of argument, say it's a probability model. So it's the semi-ring of non-negative reals. And it has a support in any case, as any distribution does. So we can always pass to the case from our full distribution with all its information about the weights in our semi-ring to just looking at whether things get valued 0 or non-zero. Now we say that a global assignment is consistent with the support of the model if its restriction to that context is in the support. For each context, its restriction to that context is in the support. So in other words, you have a model, you look at the possible assignments in the support. So that's just a set. So we just, as it were, we're going Boolean, regardless of what even if we're in full information, we're interested in probabilities. We can always just go Boolean and look at those things that are regarded as possible by the model, have non-zero weight. And we could say that a global assignment is consistent with the model if its restriction in each context is in the support. Okay, so that's a useful notion, because now we can define the model to be logically contextual if there is some possible local joint outcome, so something that is in the support at some context C, which is not accounted for by any global assignment which is consistent with the support. So there is no such T which would give us back this particular local section S. I hope that's clear. So geometrically, this is saying that some local section cannot be extended to a global one in a way that's consistent with the model as a whole. So we fix some of the values in the local section. There's no way of assigning values to the other variables, which then fits with the constraints imposed by the model as a whole. And you can equivalently, that's saying that we can't cover the whole support of the model by the set of consistent global assignments. So if you have a consistent global assignment, you can get a family of local sections by restricting it to the context. So you're going to hit some of the local sections, but what we're saying is you can't hit all of them in this way, in this case. So in this case, we say that the model is logically contextual. So this is actually the essence of Hardy-type arguments. The Hardy-type arguments are pointing out that logically contextual models are realized in quantum mechanics. We can find particular states and local observables which will generate predictions, an empirical model, a table whose support will satisfy this property. But it's just not possible to account for all the locally observable behaviors in terms of global assignments. That's in principle a stronger property than just saying that there's no sort of probability distribution on all the variables, because it implies that property. And actually, the Bell table that we started off with, that we discussed at some length yesterday, although it does exhibit non-locality as we saw, does not exhibit this stronger form of logical contextuality. If you look at the support of the Bell table, it is possible to cover everything in the support by means of consistent global assignments. So we see a hierarchy starting to emerge here. So this is the notion of logical contextuality. We say logical because the condition is expressed purely in terms of the support, independently of the actual weights, the actual probabilities which are assigned. And we say that a model is strongly contextual, we could say maximally contextual, if its support has no global section. That is, there is no consistent global assignment at all, which is an extremely strong property, saying that no possible joint outcome is accounted for by any global section. That's an almost hideously strong property, and obviously this one implies that one. And again, it turns out that there's a strict hierarchy here. This is a strictly stronger condition than that one. So, we have the Bell model is non-local but not logically. I've now switched to saying non-local here. If we think of Bell scenarios, then that would be a reasonable terminology. It's the same definitions. So the Bell model is non-local but not logically non-local. The Hardy model, that we also looked at yesterday, is logically non-local, which is essentially what we proved yesterday, but it doesn't satisfy this stronger property. If you go back and look at that support table, you can find a consistent global assignment, which is consistent with the support of that table. So we get this hierarchy here, and actually this hierarchy is all witnessed within quantum mechanics. So the lowest level is witnessed by the Bell table, which we already looked at yesterday. The middle level is witnessed by the Hardy model that we looked at yesterday, and in fact the model arising from the GHZ state with 3 or more parties is strongly non-local. So that extremely strong form is also witnessed in quantum mechanics. So the GHZ, why that's happened. The GHZ states are kind of generalizations of the Bell states. So they're these highly entangled states where either everyone is spin up or everyone is spin down, like in the Z basis. And this can be defined in any number of parties. So in the case n equals 2, we get the Bell state, and for any n greater than 2, we have one of these GHZ states. One of the interesting points to emerge from this from recent research in quantum information, and it's brought into focus, I think, in this kind of discussion, is the qualitative difference that emerges when you go from bipartite to n-partite, n greater than 2. Different things start to happen. And in some and this is interesting and slightly ironic, because by far the majority of the attention in the literature to date in quantum information and quantum foundations has been focused on bipartite systems. And it's been found that it's actually, it would generally be agreed that the understanding of multipartite systems beyond 2 parties is still very limited. And it may be that it's not entirely unconnected with this fact, that we'll see some evidence for shortly, that actually the bipartite case is not an accurate reflection of what happens beyond 2 parties, that different things start to happen when you have more than 2 parties. And we can already see here that, in fact, the behavior of the Bell state is very different from the behavior of any of these states once we allow more than 2 parties, and then we usually call them GHZ states. So what we're doing is we're measuring just in, then thinking of the Bloch sphere, we have the x-axis and the y-axis, so we're measuring these particles, and each of the n parties, Alice 1 through Alice n, can choose either the measure in the x direction or measure in the y direction. Each of these vectors is described by so for x, as we saw yesterday, they look like this, and for y, they look like this. So really, the choice of which measurement, and this is the spin up Yeah, so the positive is the spin up outcome and the negative is the spin down outcome. So once we choose the measurements and the outcomes that we're interested in, the relevant difference is the sort of whether it's plus, whether it's which of these four values is being used as a relative phase on the second term here. And you see that this is all coming from the multiplicative group of I, which is just this cyclic group C4. And that's controlling the behavior of the GHZ models under these choices of measurements. So what behavior does it give us? We can actually specify this logically. So this is realized by this geometry here, that the actual specification of the relevant behavior could be done in this style. We're saying that if the number of y, so you see that it's all, there's sort of some mod 4 arithmetic that comes directly out of this, and hence we get this sort of condition here, that if the number of y measurements, so we have a row of measurements for the n parties, each one is choosing either an x measurement or a y measurement. We see that if the number of y measurements is a multiple of 4, the number of ones in the outcomes has to be even. That's what we realize by expanding out the same kind of calculation that we were looking at yesterday. And on the other hand, if we're in the other residue class mod 4, the number of ones in the outcomes are odd. So we get this parity distinction based on where we are mod 4 with the numbers of measurements. And just from that data, we can conclude that this family of models for all numbers of parties greater than 2 are strongly contextual. Actually, there's a uniform argument, and again, this is slightly ironic because Mermin's instruction set paper exactly was about the GHZ argument in the case n equals 3. And that case turns out to be, you have to do a slightly laborious case analysis. Once you go to 4 and beyond, you can have a simpler uniform argument. The n equals 3 case is somewhat atypical. So anyway, let's consider where we do have a multiple of 4 to make things easy. So bearing in mind that we have these constraints on the support table, and by the way, all the information is in the support because the probabilities are all uniform. So as long as you know what gets probability non-zero, you just take the uniform probability on those. So all the interesting information from these models is here. So let's start off with the row where we're taking y measurements at every part. And I'm assuming here that n equals 4k. We sort of flip parities around to deal with other cases. So if we take a row of all y measurements, the number of, so I'm talking about red and green outcomes. I mean, it's 0 or 1. It's the same thing as we've been discussing. The number of red outcomes, say 0 outcomes, has some parity p. And then under this analysis, if we flip 2 of those measurements, any 2, then the parity has to flip. That's what this condition is telling us. Right? So if I replace any 2 y's by x's, we change this residue class mod 4, and hence we get the opposite number of R outcomes under the assignment. Thus, what that tells us is if we pick out any 2 of the y's from that row of all y's, which happen to be assigned the same value, and when I say assign the same value, I'm assuming that we have a global section. The global section, in a context-independent way, assigns a value, 0 or 1, red or green, to every variable, all the xi's and all the yi's, and has to work in such a way that it's consistent with what we see in every row of the table. Okay? So whatever that did, it either, given any 2 particular y's, it either assigned the same value or a different value. If it assigned the same value, if we substitute x's in those positions, to be consistent and be in the support, they must receive different values. And similarly, if it assigned different values, then if we now consider x's put in for those, again, for this assignment to be consistent with the support, they must receive the same value. And now it's fairly easy to derive a contradiction from this assumption. So if we assume that not all the yi's are assigned the same value, then we have three of these where one is assigned the same value as the other and the third must be assigned something different. So this is where it's useful to be up here. So then, of course, now we're using transitivity of equality. So yj is assigned different value to yk, but yi was assigned the same value as yj. So it also is assigned a different value to yk. Then you see that xi is assigned the same value as xk, xj is assigned the same value as xk. By transitivity, xi is assigned the same value as xj, yielding a contradiction. So with what we saw here. And then the other case is where they all receive the same values, but then any pair of x's must receive different values, but taking any three x's, since there are only two values, we get a contradiction. So there's never, for any of these models, any consistent local assignment. So what we can do is to lift this hierarchy. So this hierarchy that we've described refers to models. In terms of quantum realizations, we saw that a model is generated by taking a state and also by interpreting the measurement labels by particular local observables in the way we've been discussing it, particular spin directions. But we can, so to speak, curry these notions and just look at them as properties of the states in themselves. And this gives a new perspective on the question of understanding the structure of multipartite entangled states, which is still, to a large extent, poorly understood in quantum information. So what it suggests is a novel way of classifying quantum states in terms of their degree of non-locality. So let's focus on these n-cubic pure states. If we fix local observables for each party, then we get a probability model in exactly the way that we've been discussing. And now the idea is we can lift properties of models to states. We say that a state is strongly non-local, or logically non-local. Sorry, strongly non-local in exactly the sense of strongly non-local we were discussing before, if for some choice of local observables for each party, the resulting empirical model is strongly non-local, and similarly for logical non-local. What we're interested in is, we can put it in these terms, given a multipartite state, find those local observables which witness the highest degree of contextuality which can be achieved for that state. So we would like to know which are the potentially strongly contextual states, which are the logically contextual states, and which are at the weakest level. And I think that partly just from directly seeing the answer to the question, partly from understanding how to do this kind of thing, it would advance our understanding of multipartite entangled states to be able to get clear answers to these questions. Now we return to the theme we were discussing earlier, which is the bipartite case is a special case. So in fact, it's somewhat anomalous. For example, we just saw that the GHZ states starting with three parties are strongly contextual. But on the other hand, as originally observed by Ray Lal, the only strongly contextual bipartite models are the PR boxes, which are of course not quantum realizable. These are examples of things with super quantum correlations. So we get a clear distinction in terms of the possibility of realizing strong contextuality at the bipartite case and the greater than two parties cases. And then we have this striking result, that if we look at the bipartite case, we get this slightly strange situation that all bipartite entangled states, except the maximally entangled ones, are logically non-local. So they're at least in the, so we know they're not in the top level of the hierarchy, but they're all in the middle level of the hierarchy, except for the maximally entangled ones, which seems a bit crazy, because after all, the maximally entangled ones should surely be as non-local as anything can be. Now, Lucian Hardy showed half of this in his original construction, actually not the very first one, but in the sort of the most widely, the best known of his papers on the construction. He actually showed that you could do this construction for any bipartite entangled state except the maximally entangled one. So that shows half of this. But of course the other half is that was with a particular construction, in other words with a particular choice of local observables. The other side is to show whatever your choice of local observables, you still can't get this logical contextuality. And this was actually shown by Shane and Carmen in some work. And there's a particularly general form that is in Shane's thesis. That's in the bipartite case. But for n greater than 2, a different picture emerges. So to sort of try and state this carefully, let's say we're looking at n-qubit pure states. So we can look at this, the set of those n-qubit pure states, which up to permutation can be written as tensor products of 1-qubit and 2-qubit maximally entangled states. So either they're product states, that would be one extreme case, or they're built up from these 2-qubit maximally entangled states, sort of numbers of copies of those informed in tensor products. And on the other hand, we have this set of those n-qubit states which are logically non-local. And the result is that every state is either one or the other. So to put it in more positive terms, it's sort of slightly tricky to state it, but put it in clearer terms, every pure state is either a state whose only form of entanglement is bipartite maximal entanglement in 2-qubit subsystems, or it is logically non-local. So in other words, except for some low-dimensional exceptions, everything is logically non-local. You can always find local observables to witness logical non-locality. And this is going to be in some papers. Some special cases where we give constructive proofs appeared in a paper with Carmen Constantine in last year's QPL, and the general result is a rather beautiful result. The ideas come from Shengang Ying, who's a student of Bingsheng Ying, who will be here shortly. The general result is proved non-constructively, which is kind of intriguing. In other words, although one proves the existence of local observables that witness logical contextuality, you can't actually construct them and hold them in your hand. That's the current state of the art. It's intriguing to see if we can improve that. Let me just finish by mentioning the cases where we do have constructive art proofs. This is what appeared in the paper with Carmen last year, which will be in the forthcoming proceedings of QPL. So here are two classes of states for which you can explicitly give local observables that witness logical contextuality. So one is an important and well-studied class, the permutation symmetric states. The states such that, so you have n-qubit states, and so if you act by symmetry, by permutations on the n tensor factors, the state should be invariant. And the standard basis for these is given by the Dicker states, which are important in various physical contexts, which look like this. And for example, the W state is a particular case of the Dicker states. So this is where you have the sort of all the things we'd say with 1, 1 and 2 zeros. And we can explicitly show using the same kind of analysis that we were looking at with the Hardy argument and so forth, that these Dicker states are logically non-local. In fact, we can even use the same kind of argument with logical Bell inequalities to give a to show that to give a quantitative estimate of the non-locality. And then using some nice applications of the Majorana representation for these permutation symmetric states recently developed by Zizhu Wang and Damien Markham, we can extend this to show that all permutation symmetric states are logically non-local. again in a constructive fashion, where you actually see what the local observables are. Now, having seen this for the permutation symmetric states, it then seemed natural to me to look at the most asymmetric states towards the general idea that everything should be logically non-local, the most asymmetric states I could think of. And having been thinking about databases, for reasons I guess we'll discover tomorrow, I thought of these functionally dependent states. So these are very asymmetric states. So a balanced state with a functional dependency looks like this. So it's an n plus 1 qubit states. We have an n-ary Boolean function. So the idea is we only take those basis terms which are in the graph of this function. Everything else goes to 0, and then we just put equal weights, equal coefficients on all of those terms. So that's a highly asymmetric state. You think of the XOR function or other logical functions and the corresponding states you would get. And what we showed in the paper in last year's QPL is that all of these states are do satisfy this property. So they are, with the bipartite exceptions that we mentioned, they are all logically non-local in a constructive fashion. Okay, so I'll stop there. But next time, I certainly want to look at some of the non-quantum ways we can apply the same kind of structures, and time permitting, one or two other goodies as well.
Are there any questions? Samson?
Well, I just had a simple question, which was, given the framework of the sheaf and pre-sheaf framework, can any of these results be understood or written in the internal higher order logic language?
I haven't seen a particularly promising use for that as yet, with the exception that there are, as I'll perhaps very briefly mention tomorrow, starting to be some applications in natural language semantics. And there it seems that, and actually interestingly there, it's natural not just to consider things going on a poset, but going on a category where it was interested in relabelings of things. And there actually I think it might be possible to apply the internal language, getting a nice way of looking at what are known as discourse representation structures, which are one of the main sort of formalisms of treatment. So that's an area where I do, but I haven't seen in the quantum realm how to make that do things for me in terms of the things I'm trying to do.
Any more questions?
You have a link between compatibility and no signaling. Now,
Yeah.
I guess from the point of view of quantum field theory, you might get asked about causality. Have you got an order structure? If you allow information transfer from A to B, how does that appear?
Yes, well that's a very good point. One could consider extensions of this kind of setting to have an order structure. One of the reasons for not having sort of proceeded rapidly to that kind of thing is that this setting, simple as it is, does seem to be a little bit of a sweet spot, as I'll try and show tomorrow, in terms of fitting a lot of situations in classical computation. So it seems good to linger a while just at this level. But I think it is very natural to look at connections with causal structure. And and perhaps we should discuss that. So,
Any more questions? Prakash, maybe you could, you want to ask a question? I was saying you could set up.
Oh,
Can I ask a question?
I actually wanted to ask a quick question. Do you have any results about non-convertibility of states from one class to another through LOCC or anything like that?
That's a good point. I think there are implicitly some, not as clear as one would like. That's a good question. I think there are some results one can read off things that are known, because in particular strong contextuality is a number of equivalent descriptions. But yeah, it would be good to get a clearer picture there. I mean, and it would be good to understand the relationship with that. One thing I say is that the that sort of classification is pretty complicated and has not yielded as much purchase in understanding the description of multipartite entangled states as one might have hoped. So in a sense, the hope is that by looking at things from a different point of view, we may get some additional insight. But of course, one should understand the
I'm
relationship.
interested in the computational power of these different
Yes,
classes, so that
yeah.
would be interesting.
Right. Well, there are, yeah, I mean, in a different sense, there are some natural computational questions one can ask about detecting conditions.
Yes.
And I will have something to say about that.
Okay, shall we move on to Prakash now, and thanks Samson very much.